Hi everyone, this will be the final video for derivative, and in this video we're gonna understand derivative using limits. And we have proved the derivatives using intuitive way, where we have divided a function into small portions and try to find the derivative or slope up at that point and combine them, and then we see the result, we tend to see its derivative. And this function we're going to prove the same thing but using formulas and everything, right? And which will make more sense how organically we can understand formula. You don't have to remember any formula for this, or maybe you have to draw those graphs and divide small pieces, right? That will be too much of ask, right? So you don't want to do that, and you can understand, and easily at any point you can derive any formula, right, using this method, using understanding limit. So let's start with the problem of limits only. So as you can see over here, this function x square minus 4 divided by x minus 2. What is special about this function is that if you input 2 in this function, you will find no solution, right? Because once you input 2, it becomes 4 minus 4, right? And then this becomes 2 minus 2 and 0 by 0. So 0 by 0 is called indeterminate form. There is no solution when you divide 0 by 0. There is no solution exists. And there is a way we can find a solution. So what we can do is, we can solve this equation. If you solve this, if you see, this is more like a square minus b square, and somehow I can split this into 2, x plus 2, x minus 2, and the x minus 2 was already there. So we can cross these terms out, x minus 2, x minus 2, we left with a solution x plus 2. So basically this function, actual function is this, but it looks like x plus 2 if you solve it, right? And one thing we know that when x is 2, there is no solution, right? So the way we have written this function, it is kind of incomplete, and using limits we can actually understand it better and give more meaning to this function, right? How we can write it in a better way using limits. So that will we understand first. First we'll draw this function on the first place to see how actually it looks. So this function looks something like this, where you can see at 2 there is a hole, like there's no solution over there. If you just pass 2 value over here, there's no solution. But we can see that it looks very near by 4. If let's say if this line was a continuous line, it must have given the solution 4, right? Using graph, actually we can understand that there is some solution. And if I just bring this line x value closer to 2, I'll find some value somewhere 3.8, 3.9, something like this. Or maybe if I start from some 3, and if I bring the value closer to 2, I'll find some solution around 4. That we can see graphically, right? How we can write in a formula way, we can basically solve this equation and maybe write the function like this, fx plus 2, something like this. And then we can say when you reach x near by 2, that is what we have done with green line and orange line. When I go very close to 2, I get a solution 4. And even so, basically if you input the solution over here as 2, you can see if you put 2 over there, 2 plus 2 becomes 4. So when actually you can solve the value over here, you don't have to draw a graph. It's just if you just solve this solution and remove the solution from indeterminate form. Like first of all, you can see if there is a denominator where x minus 2, if you just input 2 over here, it becomes 0. So there is no point of. So somehow I have to solve this equation, and if I could solve that equation and bring it in a form where I don't have nothing much left in denominator, and if you just input the value x over there, you will find the solution 2. Although they both are same equation, but still this and this is different, right? This equation says there is no solution as 2. So how we can write? We can write over here limit x tends to 2 whenever. So you have to add this extra information. So this limit line actually helps you to. So this is a limit is nothing. If I have to define limit just like we have adverbs, right? In English we have adverbs, which basically verb is already there and you add some extra meaning to it. It's become adverb. Same way it is function, then it becomes limit function. Limit function, basically function has this extra information, that this extra information is this: when you go x closer to 2, there you will not find a solution, but using limit you can write when x tends to go closer to 2, you will get this 4 value, right? So you can either write fx x square minus 4 divided by x minus 2 and this line when x limit x tends to 4, or maybe you can just replace this fx with this function, or maybe solved function x plus 2, something like this. Both will work. So this one will actually not work, because if you input and solve it, you will not get solution. But if you use this function, that will make more sense, and you can write when limit x tends to 2, and that function becomes x plus 2, and if you input x as a 2 over here, you'll get the solution 4, right? You can see graphically as well. So this limit might look confusing, but it helps for a situation where there doesn't exist a solution and we have to go very close to this thing. And why it is helpful for derivative? Because in derivative we have learned that the more bigger chunk I pick in a function, I try to find the slope for this, I get more inaccurate solution, because the tangent line doesn't overlap with the function's line and there is some error. But as soon as you bring that gap, if you try to find the slope of very small tiny portion of that function, the tangent line overlaps and you tend to find a very accurate solution. So we wanted to go very close to, we don't want to go zero. Like if the difference between becomes zero, then again derivative will also come into 0 by 0 form as for this case, right? 0 by 0 form. We don't want that. We don't want to find derivative. We need a tiny bit of difference, right? We need some value in numerator, some value in denominator, rise over run to get the slope. And if I go very close to 0, I'll not. So if I have to find derivative at this point or some single point, we cannot find it, right? Using normal derivative like slope method, we need to take the advantage of limit. Limit will tell you, hey, you don't have to exactly go to that point, but very close to that point, and then you can have some value, and then you can have some value to solve in numerator and denominator. That we'll see next, right, if you don't understand that. Yeah. Before going that, we want to find slope at a point. Like this is a function x square minus 4x. We'll draw the function, and we want to find the slope at value x, where the x is 3, right? And how we can do it, we can see. This is how the function will look, and if I have to find the value over here, right? So this point is, so we can use this function, right? How we can find, so this is a function. If I have to find derivative, I'll basically, whatever the value I'll get, like let's say if I input x over here, and I'll get some value minus the 3 value, right? So what I can do is start with a big chunk, right? Let's say I pick this between 3 and 5, and I try to find the derivative of this big chunk, right? And the derivative will become rise over run, right? So dy part is 5 over here, and this difference is 1 by 4. If I find the derivative of this big chunk, I'll get a solution that will become 3.14, right? But our goal is to not find the derivative of this whole thing. Our goal is to find derivative of this point. So in numerical way, we can write there will be some point x somewhere over here, and then this point, this thing, right? And if I find their difference, so this basically represent the rise part, and this represents the run part, right? And if I divide it as close to 3, when x reaches very close to 3, right, then what happens is that this distance comes down very close, and you can see there are some gap between this tangent line and this function. But as soon as we go very close, this tangent line overlaps. Now we can't even see the white line. It has totally been covered with the red line, just like a lunar eclipse or something. So they are basically each other right now. So at this point, if I find the derivative, that will give me the derivative at this point 3, right? And we can solve it. If you find, just divide this thing, you'll get the slope around 2. But you can see that when this function was over here, right, you can see the slope is coming very close to 3. Whenever this function is going very close to 3, when the input is going very close to 3, then this x values is going very close to 3, my slope is coming very close to 2, right? So using derivative, we can actually find, and you can see from the graph as well, and if you can solve it over here, right? If I solve this x function over here, and x minus 3, and this fx3 will basically give you the value 1 that you can write over there. And if you solve this thing, and now if you just input 3 over here directly, it is in indeterminate form. 3 minus 3, the difference is 0, right? So over here we are not approximating the solution. Usually whatever previous methods we were approximating, like, oh, it has to be very small. We are not doing. With limits we can actually remove that approximation and get an exact solution. So as you can see in the previous example, how the solution doesn't have a solution where x is 2, but when we solved that solution, we exactly got the solution 4 over there. Same way we can solve this part as well. And when you solve this thing, this x square minus 4x plus 3 using quadratic method, you can find x minus 3, x minus 1, right? and then x3 minus 3 can be get cancelled, and we are left with x minus 1. So with approximate method we can see the solution was going to problem, but we can exactly get a solution if I just solve this function. Once I solve this, x minus 1 becomes 2. So you can see two kind of solution. One is approximate way, and using limit we actually got. So limit, what did limit help this over there? Instead of inputting the value directly in this thing, you'll get a solution 0 by 0, which we doesn't want. But when you solve this equation little bit and you reach a point where your denominator is not there, and you go to a simple formula. So this whole function was represented like this thing. This whole difference was represented x minus 1. And you have to just input 3 over there, and 3 minus 1 becomes 2. So this is a more clearer picture now, right? How we can find slope at any point using this formula. You don't have to approximate. You can just exactly get as answer in a very whole number instead of having a decimal or something like this. And so, but problem is that we are doing it for single things, but what we want to get a generic formula, right? Generic formula to find derivative for any function. This previous function was x square minus 4x plus c. So this time we don't know a function. We want to make a generic formula for any function. We can do it using limits, find the solution, right? So in this graph, as you can see, we have a point PQ, right? And if I have to find derivative between P and Q, right? So we have to find the distance rise, basically this part, and overrun. So this P part, basically this point is called X, and if I just add a small distance delta X over here, this point will become X plus delta X, right? X is already this point. Maybe let's say imagine X was 3 and the small distance was like 2 or something. So X plus delta X become 2 plus 3, 5 somewhere over here, right? So this represent X plus delta 5 because this distance between this green point and the orange point is delta X, right? And if I input to the function, I'll get the fx, right? As the notation say, this is pink line is the function. If you input something, this will look fx, right? And so we are, instead of getting a solution, we are writing in a variable form so that we can create a generic formula for derivative. And if you input x plus delta x, the output will be fx plus delta x, right? As we have learned this thing in the functions a lot. So this difference between orange and green line, difference will be basically fx plus. So if I have to find the slope of this thing, the formula will be something like this. This difference, right? Rise minus run. So if you differentiate fx plus delta x minus fx, that is there. And if you find the difference between x plus delta x minus x, so this x will get cancelled and we were only left with delta x. Basically, the slope is saying this tiny distance over here from green line to green line. Although in this example, we have taken a big distance. And this will be the basically slope of this PQ line, blue line, not the pink line, right? And our goal is to find a generic formula, maybe say for this point or something like this. And if I just bring this PQ line closer, at some point it will overlap the exact function. And at this point you can see the derivative of this area is same as the derivative of function. And if you go closer, it is exactly, right? So if you see, the difference becomes very minimal and we'll get a more accurate solution. But still this is the derivative for PQ. But if I have to find derivative of this point at x, so we can say that when x reaches this delta x, derivative at this P point, which we can say this point is x, like in general, because of this x, the value x is over here like around 3 or something like this. We want to find a generic formula. That's generic formula we can write in terms of x, right? So this x, we can say that when delta x becomes 0, right? You can see the difference is going very small. That time, the solution will be fx plus delta x minus x by delta x, right? And we don't know what kind of function. It looks like a square function, something, right? So this is a generic formula at any function. Like if you use this formula at x, where the delta x becomes 0, this is a generic formula, fx minus delta x, something like this. So this is a generic formula. What is generic formula means is basically, when you replace this function with any function, maybe a square function or maybe a cube function, and use this same formula, if you solve that formula, right? Because right now if I just solve this limit, delta x, this will become 0, and then 0 divided by anything, we will not get a solution. But if we solve this equation little bit, where the delta x has to be in denominator. And then if you apply delta x is equal to 0, that time you will find a solution. If you're confused, you will just understand it by the next example. So we can use this formula which we have learned to find the derivative at any point at x. So if there is a function at any point, we can find using this formula which we have just derived right now, where the difference between the numerator and denominator has to be little, which is represented by this thing. Delta x has to be very small. When the input is small, your output will be also very small. And my function is x square. So just replace this thing with x square. So this becomes delta input is x plus delta x divided by the, basically I'm replacing this f with x square. Again this, so this will become x square and this will become a plus b kind of whole square of thing. Like this looks very similar to a plus b whole square thing, right? And if you solve this thing, it will become x square plus 2x delta x plus delta x square minus x square. So if you see minus x square can get cancelled, and we left with 2x plus delta x and the delta x square. And as you can see, delta x is common over there, that we can segregate, and we can take this delta x out, and we can then basically they both are we can cross this delta x and this delta x and solve it. Now the equation is in a very good form where we don't nothing have in the denominator, and now if I just input this delta x to be 0, I will left with 2x. So this gives the solution. So whenever if you want to find derivative of any point, so if you have a function x square and you want to find derivative at any point, maybe at 3, 4 something, you don't have to like input 3 and then you have to find some difference, then you have to find the fraction, the rise over and divide it, right? But we have made a generic formula using those tools only. So this generic formula look like this. Once you input any function, you will get the solution, right? Over here you can input even x cube as well, and then solve it, you will get the same solution. What will be for x cube? So that we'll see in the next slide. For x cube, again the common formula which we have derived using limit, and you can apply the x cube, the formula. If you solve, this becomes very big. This x cube minus this can get cancelled, this become, then you find this delta x common. Once you find delta x common, if you put delta x is equal to 0, so this becomes 0, 0 multiply by anything becomes 0, this becomes 0, so you're only left with 3x square. So the solution for x cube. So what is the derivative for a function which looks like x cube? Derivative at any point will become 3x square, right? So this is how we have derived the solution for different trigonometric functions, even log, cosine, whatever, right? Same way you can replace this log function or cosine function. So that could be the homework or exercise for you to find the solution using this method, right? You just replace, we call it finite difference, right? And a lot of books or something you will learn about people calling it finite difference, which makes sense because we are trying to find the difference over here. This is finite difference method, and we can substitute any function over here, right? If you replace sin x plus, then you have to know your trigonometric function. What will the solution when we have sin a plus b, right? You must have seen this formula. So then you solve this thing and then you subtract one of the sin x and then get cancelled and you will left with cos x or something like this. So goal is to, the homework is to go through that, and I hope you have understood it. If you understood it, you will probably able to solve it. And if you have any problem, write in comment section. I hope you got a lot of value from this video. And this video, now we have reached a very good point. Now we have understood derivative. In the next few videos, we will learn the applications of derivative. We have understood the theory, where the derivative is actually used. Instead of solving it in an exam, these big equations, and we solve it in exam, and that is not the goal of derivatives. There are so many good examples, real life examples. There is so much examples in the AI, right? How the chat GPT and these all things are very smart nowadays, right? How it is used in machine learning models. So, go and touch upon that in next video. Or right now, if you have any tool or something, just you can take the screenshot and search in ChatGPT and ask, hey, similarly using this this kind of method, do it for sin x, cos x, log x or whatever, and they will use the same method and they'll substitute a lot of things and solve it for you, and you can see the solution. So I hope you like this one. Do subscribe me because a lot of interesting videos are coming, and this is a part of series. If you're not able to make some sense or something, like maybe I am referring a lot of things from the previous video, so that those are kind of prerequisites. I hope you go through them as well. Otherwise, if you understood, that's well and good. So see you in the next one.
Who are you? My guy! I'm gonna become stronger than anyone.